Okay, so yes, my name is Declan Carroll. I'm going to present some work on while I was in Imperial. I'm back in TV now, so I'm confused as to where I'm supposed to be. But I'm going to present on some fracture toughening of carbon fibre reinforced polymers modified with rubber and silica nanoparticles. So, first of all, I'll go through the materials that we used, looking at the resin mixture and also the nanotoughness. Quickly go through the experimental methods, mechanical properties, and fracture. We'll take a look at the morphology. So, one of the key things about getting good toughening in nanotough materials is to get a good dispersion of the nanoparticles. If they all come together, you don't get generally good results. So you want to get them reasonably well dispersed. We'll take a look at some results, a little bit of modelling studies and insights that we can gain from looking at the modelling studies, and then finally we'll conclude. So, I used an epoxy polymer, which was an anhydride cured DGBA. I mixed in this with a reactive diluent, which lowers the viscosity of the epoxy, which allows it to be used. It allows it to be used much easier for processing in terms of carbon fibre infusion technologies. So the reactive diluent used was DER 734 from Dow. It was basically we replaced 1/4 of the resin with this reactive diluent, and we used anhydride hardener HE600 from Evonik. Material cycle was 90 degrees 1 hour, and then 160 degrees for 2 hours. TG of these systems is about 130 degrees. So, what nanoparticles did we use? Well, we used some silica nanoparticles and some core shell rubber nanoparticles. So the silica nanoparticles were obtained from Evonik at 40% weight, pre-dispersed in the resin already, which makes things easy to work with. So the silica nanoparticles have a relatively narrow side distribution. We can describe the distribution as nearly normal. So about 95 to 98% of the particles have a diameter between 5 and 35 nanometers. So they're very small particles. The core shell rubber particles have a lot normal size distribution. Here, the mean particle diameter is about 160, but we do see some particles up at half a micron, but not a whole lot of them. So these core shell rubber particles were also obtained pre-dispersed in the DGBA resin, and they have a cross-linked polysiloxane core and a thin skin of epoxy functional groups on the edge. They're not really core shell rubber, they're more kind of core skin rubber. They don't have like a lot of core shell rubbers have an actual PMMA shell, but these just have kind of a skin of functional groups on the end. So, we'll take a look at AFM now and the mechanical properties. We'll quickly go through tension and compression properties. Focus most of my talk on the fracture properties, so single edge notch bend tests for the bulk polymers and double cantilever beams for the carbon fibre reinforced polymers. And then, of course, when you do a fracture test, one of the most important things to do is you have to look at the fracture surface, because the answer to all of your confusing results is always on the fracture surface. We just need to learn to understand the language of the fracture surface. So, morphology. On the left-hand side, I have a typical morphology from an AFM image of what happens when I add 8% core shell rubber particles. So we can see the CSR particles, and they're reasonably well dispersed. And then on the right-hand side, I have an image with 8% CSR particles and 8% nanosilica. So we look here, we can see some little yellow dots. They didn't come out too well on the screen, but there are some little yellow dots here, which are the silica nanoparticles. And so we're reasonably confident that there's a good dispersion of CSR particles in both the case of CSR on its own and also in the hybrid case, and also the silica nanoparticles are reasonably well dispersed throughout the remainder of the matrix with CSR in the hybrid case. So, quickly go through some tensile modulus results, and it's no surprise when we add the silica nanoparticles to the epoxy, the Young's modulus of the silica is about 7 gigapascals, the Young's modulus of the overall bulk polymer composite goes up, and when we add the compliant CSR particles, the Young's modulus of the composite goes down. I must point out as well that we did all these tests at about 20 degrees, so nominally room temperature, so 20 plus or minus a couple of degrees, and also at minus 80 in a liquid nitrogen chamber. So the more exact model I've included as well for both the predictions, and they offer a reasonably good prediction of what the actual composite modulus is. The dashed lines are the results at 20 degrees, and the solid lines are the results at minus 80. So one of the things we can see here is that the modulus actually doesn't change all that much between room temperature and minus 80 degrees. So, With tension, it's very difficult to actually get the full stress strain curve because the sample usually fractures just post-yield or definitely in the strain softening region. So we turn to plane strain compression to get the full stress strain behaviour. And on the left-hand side here, I have an example image of a 20 degrees, the blue line. So we see initial elastic region, followed by yield, followed by a strain softening region. This here was when the sample actually cracked a little, so you get a slight loss of constraint. But then the sample then strain hardens, and then you get final ultimate failure. So we can record the true strain to failure. Okay. When we go to minus 80 degrees, we see that this strain softening region has disappeared. Also, the yield stress is no longer defined upper yield stress, but the yield stress, 0.2% proof stress is about 160 megapascals, so it's much higher than at 20 degrees. And this test here as well did go to ultimate failure. We expected to go on up here because the low limit of the machine was reached when we got to about 260 megapascals. I did these tests in a 150 kilonewton machine. So, on the right hand side, I have some tension compressor tests at room temperature. What happens when we add silica? What happens when we add CSR? When we add CSR, we see that the CSR particles reduces the yield stress and also reduces the amount of strain softening afterwards. You don't get as big a drop in the stress post-yield. The addition of the silica nanoparticles does practically nothing. It doesn't really change the yield stress, it doesn't really change the post-yield behavior. And this will become important a little bit later on. So let's have a look at the fracture energy of these both polymers. On the left-hand side, I have 20 degrees, and on the right-hand side, I have minus 80 degrees. So we'll concentrate on the left-hand side first. The first thing we can see is that when we add silica, so 0%, 4%, and 8% silica, when we add silica on its own with 0% rubber, the silica really does nothing. We get an increase from about 125 joules per meter squared up to about 170. So adding the silica at room temperature really does nothing. When we add the CSR particles up to 16 weight%, we see that we get an increase of almost a tenfold increase at 16 weight%. And there seems to be a reasonably linear trend, at least up to 8%. When we add in CSRs and silica together, we see that actually the silica tends to enhance the toughenability of the CSR. So the hybrids are actually, the hybrid materials have some synergy associated with them at 20 degrees. So the difference between this value and this value is about 350 to 400 joules per meter squared, whereas just with the silica on its own, we only get a difference of about 40. So by adding the two together, we're actually seeing a synergistic effect. When we go to minus 80 degrees, the first thing that we can notice is that adding the silica actually seems to have a beneficial effect. We're getting quite a substantial twofold increase here. But that we don't see any of this synergistic effect where these lines are diverging. These lines are pretty much parallel. Okay, so adding the silica at either 4% or 8% does have some toughening effect, but adding more of it doesn't seem to increase the toughening effect, and then adding it as a hybrid also doesn't seem to increase the toughening effect at minus 80. Okay, so let's have a look at the fracture surface of the CSR modified bulk polymers. On the left-hand side, we have the room temperature 20 degrees. On the right-hand side, we have the minus 80 degrees. So we can see that all the CSR particles are cavitated at both 20 degrees and minus 80 degrees. Slightly rougher surface here. There's void growth observed on the surface. So if you measure all these voids, they're on average bigger than the particle size. So that indicates that particles have grown. This is a major toughening mechanism. And interestingly, the measured void diameters at minus 80 are greater than at 20 degrees. So then why is my material not tougher at minus 80 degrees than at 20 degrees? This is actually not necessarily indicative of a tougher fracture response, because while the work done to around one void is equal to the integral of sigma dot the epsilon, the actual size of the plastic zone is much smaller because we have that much higher yield strength, and that's proportional to 1 over sigma squared. So actually with the higher yield strength, we end up with a less tough CSR material. We move on to the silicon modified materials. With 16 weight% on both sides at room temperature, we see that at room temperature and at low temperature, we see that there's no debonding of silicon nanoparticles in either image. The fracture surfaces have a typically brittle appearance. These fracture surfaces appear a little bit rougher, so obviously a rougher surface is an increased fracture area. So this may contribute to our observed increase in fracture toughness from earlier on. But just actually summing up the area contribution, like in the Faber and Evans paper, doesn't actually account for everything. So see that the fracture energies of the carbon fibre polymers are much higher. So our control system, which is the blue dot here, is at 1250 joules per meter squared. So our fracture energy of the carbon fibre polymers are much higher than the corresponding bulk epoxy polymers. This is due to the influence of the additional fibre toughening mechanisms, but also that when we add in the CSR particles and also the silica particles, we do see some toughness increases. So there is some transferability of toughness from the bulk polymers into the composite systems, especially at 20 degrees. At minus 80 degrees, we see that this is our control. Here we have a drop in fracture toughness of about 300 joules per meter squared down to about 850, and adding in the other material, adding in the modified matrices causes an increase in the fracture toughness, but it's difficult to figure out whether there's any benefit in adding in hybrid materials, because they all seem to just be independent. Adding the tough matrix just appears to be independent of the amount of CSR particles or silica particles that you add. So the last point to note as well is that like in the bulk polymers, the CSR particles, the composites, are tougher at room temperature than at minus 8 degrees. So this should be no surprise. So one of the ways to look at this is actually to plot the bulk material fracture toughness versus the composite material fracture toughness, and these dashed lines are slopes of 1 to 1, indicating that if your data lies along these slopes, it indicates that there's a perfect transferability of toughness. So we see that the black point here is our control, and when we add the silica, we actually don't really see any transferability of toughness. But when we add the rubber, so the toughness of the composite goes up when we add the rubber. There's not really a huge change in toughness when we add silica. And then at room temperature as well, we can see, or at minus 80 degrees, we can see that as we add in the silica and the CSRs, we get an increase in toughness of the composites, but we don't really see that there's any kind of actual trend, because the error bars of the carbon fibre is masking basically what's happening with the matrix. So the increase in toughness in the matrices is approximately the same as the error bars within the composite. So the synergistic effects of the hybrid bulk polymers is not transferred to the CFR piece at bulk test temperatures. We see here that as we go on the bulk, we go 0 for 8, whereas it goes 0 for, and then adding 8 silica actually makes the response of the fracture toughness of the composite worse. So the behaviour of these carbon fibres is dominated by the fibre-induced toughening mechanisms, but adding in the modified matrix does increase the toughness of the composite at both 20 degrees and minus 8 degrees. So we take a quick look at the fractography. So we can see that we have carbon fibres, and these carbon fibres are relatively clean. So this indicates that there's pretty poor adhesion between the matrix and the actual carbon fibres. So we see some fibre matrix debonding, and then we possibly see some debonding of the silica, but we're not 100% sure in that case. In the CSR modified materials, it's much more clear. We can see void growth cavitation. So this indicates that when we look at this surface, we see the cavitation and void growth. So then it's basically the samples the toughening mechanisms are being induced. And then the fracture mechanisms on a growth scale are dominated by fibre fracture, fibre pull-out, and also fibre bundle bridging. So this is a picture of some of the most excessive fibre bundle bridging that I saw in my tests. And then I'll quickly just go through some fracture energy modelling. So we used the Fine-Kinloch model, which was from about 1992, which says that the overall fracture energy is the sum of the resin fracture energy plus the toughening mechanisms from the particles, which can be identified as localized plastic shear banding and also plastic void growth. These are the equations that were worked out by Fine-Kinloch back in 92. All of these can be measured. Particle volume fraction can be measured. Compressive yield stress was measured earlier. Toxic failure strain was measured. This is a fitting function from Fine-Kinloch and later modified by Say et al. And we can measure the void volume fraction, and we measure the plastic zone size to unmodified epoxy, and then the stress concentration factor, which we take. It's different depending whether it's a hard particle, soft particle, or a void. And when we have the hybrid polymers, we have the toughening increment can be expressed as basically the sum of the toughening due to the silica and the sum of the toughening due to the CSRs. We didn't see any foil with the silica, so that's 0. So I have an example here of our measured and our predicted. So we have reasonably good prediction when we go from 4% CSR and adding in the hybrid materials, 4% silica and 8% silica. And what we see actually is that the presence of the silica, while it doesn't add a whole lot to the actual toughness, we see that what it does is it enhances the ability of the CSR voids to grow. So what the actual presence of the silica is doing is it's providing a synergistic response. It's allowing the voids generated by the cavitated CSR particles to grow much better. So in conclusion, quick conclusion, I've run a minute over time. Silica and CSR nanoparticles have been put into an epoxy polymer. Good particle dispersion. They toughen at both 20 and -80. They're better at toughening at 20 degrees. Toughening mechanisms were identified, and we see that there is some benefits to adding hybrid materials and hybrid toughened epoxy matrices to composite materials, but fibre toughening mechanisms are still dominant. Thank you very much.